Last video we looked at how we can write Kc, the equilibrium expression for equilibrium reactions, and what it means. So just to remind ourselves, if the Kc number is greater than 1, it's favouring products, but if it's less than 1, there are more reactants than products. Most of you asked about what to do. Well, how do we calculate this Kc? And that's what we're going to look at in this lesson. So, if we're given an equation like this, here's an equilibrium reaction, carbon monoxide with water reacting to make carbon dioxide and hydrogen, and we are given concentrations for these gases or concentrations for these aqueous solutions, just reminding that in our Kc we don't include solids or liquids. Then we can calculate Kc. The first thing we need to do is write the equilibrium expression. Key thing again is that we've got the products. Some ways and always writing as a R, but the products over the reactants. Alright, once we've got that, all we have to do is put our numbers in and then solve it. Just remember that these are multiplying and that we, in our calculator, we will need to put these in brackets after we put the divide sign in there to get it to work. Now if we do that, we get the number 400. And what does that favour? Does that favour the products or the reactants? Here's another example. So here we've got nitrogen and hydrogen reacting together to make ammonia, and we get given the concentrations. First step, we need to write our Kc, products over reactants, raised to the powers. Remember now we've got powers, we've got 2 and 3 there because of the 3 and 2 written in front. Then we just put our numbers in and solve. Again, making sure we've got brackets down here, multiply them together, and that these numbers are cubed and squared appropriately. If we do that, we end up with 0.0185 for the Kc. Now that's less than 1. What does that favour? We can also use Kc to compare with some given concentrations as to whether the reaction actually is at equilibrium or not. So here is a potential question. I've got a reaction of hydrogen reacting with carbon monoxide to make methanol, and our Kc is 280, which means it's favouring the products. Now here are my given concentrations. They're actually moles, but if they're gases and they're in 1 litre container, then it's just divide those by 1 to get moles per litre. So we need to justify whether the reaction would proceed forward or reverse when the gases are mixed, which is basically asking, is it equilibrium? And if the number I get out is less than Kc, it'll go forward. If it is greater than Kc, it'll go backwards. So first step we need to do is write the equilibrium expression. Done. Next step is to put the numbers in and solve for it. So here are the concentrations put inside the equation. Again, make sure we've got these in brackets and they're multiplying together. And if I do that, I get out 0.8. Now you note that I'm using Q here. Now it's just a funny thing, because we're putting in these concentrations which may not actually be the equilibrium concentrations, we use a separate letter rather than QC, which is for when it's at equilibrium. We use something called Q, reaction quotient. So that's for when we're just putting in some random concentrations to determine whether it's at equilibrium. So I've got Q here and it's 0.8, and the last step is to compare it with Kc. And Kc is 280, so 0.8 is smaller than that. That means I must need more products. So the reaction's still going to go forward and make more of the methanol, more of the products. before it will reach the Kc of 280. So that's one thing we can do with our Kc value. And we'll do one more example in this case. So here we go. First step for this equation, even for really analysing it, I know I have to write the Kc. So Kc equals, and then I've got products, so H2 to the power of 4 CS2 over H2S squared times by methane CH4. Alright, so I've got my Kc. Now I want to work out my Q, my reaction quotient, with these concentrations. Going to see if it's in equilibrium or if it will go forward or reverse. Now I've made it a little bit trickier because this is now in a 2-litre flask rather than the 1-litre flask. So if I want to get the concentration, it's moles divided by litres. So I'm going to divide these by half or by 2 to get the new concentration. So I'll do that at the same time. So 0.8 moles of 2 litres is 0.4 to the power of 4 multiplied by CS2, which is now 0.25, divided by 0.005 squared multiplied by 0.005, and when we do that, we come out with an insanely big number of 102,400. And since Q is greater than Kc, that means that the reaction is going to proceed. Reaction is going to go in reverse. Because there are too many products and not enough reactants. Another way we can use Kc is to calculate for an unknown concentration. So if a reaction is at equilibrium, we've got some concentrations but not others, in the Kc we can actually then go and find that missing concentration. It's essentially algebra. So if you like algebra, you'll enjoy these. If you find it's a bit harder, it's going to be a bit more challenging, but certainly give them a go. Certainly, you must, if you get one of these, at least write down Kc. So that's our first step, Kc. So Kc is products over reactants raised to the power of their coefficients. First step. Now, I need to find out what carbon monoxide's concentration is. Right, because these are going to equal 280. So, what I can do, since I know my algebra, is that if I, let's put Kc still there. If I have this again, and if I multiply this by carbon monoxide and multiply both sides by carbon monoxide, then those will cancel, and that will equal carbon monoxide times by Kc with methanol, and like so. But then if I divide by Kc and divide this by Kc, essentially I've rearranged it to this, where if you look back to the top one, in this case I've essentially just swapped them. Now I've rearranged it, then I can solve it. I've just got to put my numbers in. So I've got my numbers, I've got 0.100 divided by 0.05 squared times 280, remembering to put that bottom one in brackets. And if I do that, I come out with the concentration of, in three significant figures, 0.143 moles per litre. Alright, let's carry on with another one. Here we're going to find the concentration of the methanol, which is a bit easier. So get back to Kc, and then what we need to do is basically multiply both sides by H2 squared and CO. So those will cancel, and you just end up with H2 squared times CO times Kc. So I am going to have Kc multiplied by the carbon monoxide, 0.5 times by 0.05 squared, and that gives me the concentration of 0.350 moles per litre. So that was perhaps a bit easier if it's on the top. And finally, the one that's a little trickier is when we want to find H2, because of the fact that you've got two of them, it's going to be squared, so that's a bit of a pain, but we can get around that. So as we learnt the first one of these sort of equations, that if it's on the bottom, we can just swap those two if we're trying to solve it. So you can do that without remembering your algebra, because it works. Oh, I don't know. Oh, H divided by Kc times by CO. Now the only way to get rid of that 2 squared is we do the square root of that, and so that will get rid of that, and we end up with this. So we end up the concentration of H2 equals the square root of these concentrations. So that, we'll just do it carefully in our calculator once we put the numbers in. So we've got 0.100 over 280 times 0.5. Oh, oops. Get that right. And if I do that carefully enough, I will get a concentration of 0.0267 moles per litre. Alright, so that's calculations. I can calculate Kc by putting in some concentrations given to me that are at equilibrium. I can determine whether a reaction mixture is at equilibrium by putting them in the reaction quotient, which is essentially Kc, and working out whether the number is bigger than Kc, then it will go backwards, or if it's less than Kc, it will go forwards to make more products. And finally, I can find an unknown concentration of something by basically algebra, using KC, the equilibrium expression, in algebra.